Hey everyone, so this is your practice exam for exam 4. All right, let's go ahead and get started. So the first question says, which of the following signs on Q and W represent a system doing work on the surroundings as well as getting heat from the surroundings? So if something's doing work, like let's say I take this calculator and I push it, I expended calories doing that, so therefore I lost the work, if that makes sense. So in that case, our work would be negative. And if something's gaining heat, that means heat is like being added on it. Think of like if I took a blow dryer and I don't know, blew this thing, it would absorb the heat, and therefore its Q, or heat, would be positive. Don't forget also that delta E equals Q plus W, in case that comes up. It's the amount of heat plus the amount of work. We did a problem in class about a car engine that let out a certain amount of heat, did a certain amount of work on the car. That's something to consider as well. Okay, number 2. Determine the specific heat capacity of an alloy that requires a certain amount of energy to raise the temperature, blah, 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 blah. All right, cool. Anytime you see something about specific heat capacity, you're thinking Q. Q equals MC delta T. That's what we're gonna always kind of go to. Where Q is the heat, but it should be in joules. So this is 59,300 joules. Don't forget K is just equal to times 1,000. So if you have 100 K, you've got 100,000. So 59.3 K would be 59.3 thousand. So our Q over here is that. Our mass is the 150 grams. And our delta T is always final minus initial. Don't forget, it doesn't matter if it's in degrees Celsius or K as long as they're both consistent. But delta T is always T final minus T initial, which would be 398 K minus 298 K, which would be 100 K. Okay. These both have these have 0 decimal places, so we would know it to the ones place, so that's why I put that decimal place there, just to remind you about sig fig rules. Okay, so let's go ahead and throw this information in here. Our Q was 59,300 joules. We're setting that equal to our mass, which was 150.0 grams, times our C, which we are solving for, times our delta T, which was 100 Kelvin. All right, so let's go ahead and solve for it. The way I do this, and I would love if you guys start doing this, is we're trying to get C alone, right? So we'll start right here, and we'll divide by 150, and then we'll divide by 100K, and that will give us our C. So in my calculator, I say 59,300 divided by 150, and then divide it by 100. Hit enter, and that's our answer. I get C equals 3.95. And our resulting units would be joules, and then we divide it by grams, and we divide it by K. In this case, remember, it doesn't matter if it's C or K, so we could have done it in Celsius or Kelvin. We would have gotten the same answer, 3.95. All right, moving on to the next one. How much energy is required to decompose 765 grams? So the first thing I do with grams is turn it into moles. So I take my 765 grams. I usually do it in the problem, but I'm kind of out of space. 765 grams. I divide it by that 137.32 grams per mole, and I get an answer of 5.5709 mole, and that's of PCl3. So under here, under PCl3, it's 5.5709. And it wants to know about how much energy. So it's looking at this over here. That's our question mark. Now to remind you, what this means, the delta H of a reaction means that if we have 4 moles of PCl3 and we react them all, we'll get 1 mole of P4, 6 moles of Cl2, and it will require 1,207 kilojoules of heat. In other words, this is an endothermic reaction, right? So it takes this heat in, plus 4 moles of this, gives us 1 mole of that, and 6 moles of this. So it's just another stoichiometry kind of problem, which should be a bit of a review. So we're starting with 5.709 mole of PCl3. Start with the thing you have, and we turn it into the question mark. If this is mole of PCl3, we know that we must put a 4 down here. For every 4 mole of PCl3, we require 1207 kilojoules. If you do this, you get an answer of 1681 kilojoules, which in scientific notation would be 1.68. Don't forget this had 3 sig figs, times 10 to the third, because we'd have to move that decimal 1, 2, 3 times. So D is our answer. All right. This next question says, use the following equation for the combustion of octane. Calculate the grams of carbon dioxide formed from 100 grams of octane. So the first thing I'm going to do is turn grams into mole. So 100 grams of octane, and it's 100.0 specifically. I'm going to divide that by its molar mass, 114.33 grams per mole. And for octane, I found that that's 0. Here, let me do it for you. 100 divided by 114.33. I get an answer of 0.87466. I'm going to keep an extra sig fig because this should have 4. So over here under our moles, we're going to put that 0.874661 mole. All right, now I can keep reading the question. It wants to know the grams of carbon dioxide. So this is going to be our question mark, but we want it to be in grams. And this is just a straightforward stoichiometry. Gives us the molar masses of CO2 as well. So we're starting with moles, 0.874661 mole of C8H18. I know for every 2 mole of C8H18, I get 16 mole of CO2. Now we would stop if it asked for grams, or if it asked for mole, but it asked for grams, so we got to continue. We know a mole of CO2 has molar mass of 44.0095 grams. So take the answer I have, times 16 times 44.0095, and then I'm going to divide it by 2. And I get an answer of 307.9 grams. So on the next page, I see 307.9 grams. There you go, if you needed to look at it a little longer. All right, so let's go ahead and move on to this next one, which is Hess's law kind of reaction, or Hess's law problem, where we kind of move things around in order to match the total equation that we're looking for. So in these situations, I like to, anytime we're given a Hess's law, so you have these and it asks you to determine some unknown, I like to kind of rewrite them because I like this total one to be on the bottom. It just makes it easier to see, but most often these kind of questions are given to you as you see it right here. So I like to say 2NO plus O2 yielding to NO2, and that's the delta H that we're looking for. But it wants me to take these two equations, the first one, N2 plus O2 yielding 2NO, where our delta H equals 183. And the second one, 1/2 N2 plus O2 yielding NO2. And that delta H equals 33. And these are all in kilojoules. Okay, so we want to be able to add these two up to equal this thing. We can manipulate these equations. Remember, we can multiply them, we can divide them, we can flip them around, but we have to have this overall at the end. Don't forget that things cancel. So if I added them up the way they are now, I would have 1.5 N2. I'd have 2 O2s yielding 2NO and an NO2. And that's obviously not what we're looking for. So we always go to this bottom one and say, okay, what do I see? So here I see 2NO. The only place where NO is coming from is up here that I see. And so it's right that it's 2, that's good, but it's on the incorrect side, right? I'd want to flip this thing around so that when I add it up, it ends up on the reactant side. So I'm going to flip this whole thing around, and I get 2NO yielding N2 plus O2. And then obviously my sign is now negative 183. So I change it from positive to a negative. I'm going to go ahead and scribble this stuff out. So probably the easiest thing to do is to forget that you flipped it, or to forget to change this, and then it was all for naught. So make sure you flip that sign. Okay, here we have 1/2 N2 plus O2 yielding NO2 on this one. So we go down here and we're like, okay, what do we end up getting? Now we have the 2NO on the right side, but the O2 over here, if I added these up right now, I'd have 0 O2. These two would cancel. So I know that that's not right. So I do something with the O2. Let's look at this next one as a clue. Here I have 2 NO2, but here I only have 1 NO2, right? So I have to multiply this whole thing times 2. So what we end up with is an N2 plus 2 O2 yielding 2 NO2. And of course our delta H, we also have to multiply by 2 to give us a positive 66. Once we've done that, don't forget, erase that business. Cool. Okay, so now when we go to add them up, our N2s can cancel. Our O2 here cancels with one of the O2s there. And we're left with 2NO plus one of the O2s yielding 2 NO2. If we add these up, negative 183 plus 66. I get negative 117. And that would be our answer. All right, moving on to number 6. It says determine the delta HF for this. So to make Li2SO4, the formation enthalpy, or delta H of formation, there are two things that we have to think about. The first one is that this one has to be a 1. It cannot be a 2, it cannot be a 3, it cannot be anything. We're forming 1 mole of this. So looking through here, that immediately eliminates this one and that one. And this one's on the wrong side altogether. We're forming it, so that's out of play. So it's just those two. All right, the next thing we know is that lithium sulfate wasn't formed by lithium and sulfate. These have to be in their elemental state. And to remind you of elemental states, N, O, F, Cl, Br, and I, these are all, and H2 as well, these are all diatomics. So I wrote them like this because this is the way they appear in the periodic table, and they also look like a number 7, and there happens to be 7 of them. And these are diatomics. Inside this number 7 is actually spooning Se, P, and S in there. And really it's P, whatever, S, Se, but I like to remember it as seps, those 3. And these 3 happen to be, the S's have 8 and the phosphorus has 4. And it's not always, but it's very often that you'll run into this. So sometimes you'll see sulfur just plain S as monoatomic, but it does form a very stable S8 structure. So going back over here, we're like, okay, what made lithium, sulfur, and oxygen? Well, it had to be lithium, sulfur, and oxygen. And oxygen happens to be a diatomic, and sulfur, you generally don't know if it's going to be an S1 or an S8. It depends, but the only thing that matches is this one right here, where it's lithium, sulfur, and O2. Notice this is not the most simplified version. SO4 has an S and an O combined, and that can't be it. You'll never be ions. So B is your answer. All right, number 7. Use the information provided for this. Okay, so here, we're going to use this table and kind of plug things in. This would be to form negative 824 kilojoules is how much it is for 1 mole of Fe2O3, but we have 3 moles. So anytime we're given this, we're going to take 3 times that amount. And then over here, our CO is just one of them. So times negative 111. And then I like to split up the products and reactants side. So over here we have 2 times the Fe3O4, which is negative 1118. And then plus our CO2, which is negative 394. So over here, let's add up everything on this side. I do 3 times negative 824, and then I'm just going to subtract 111, and I get negative 2583. So add up everything over here. We do the same on this side. 2 times negative 1118 minus the 394, or you could have also done plus and negative, and I get negative 2630 kilojoules. Okay, so right now I have my total on products, total of reactants, and just don't forget that delta H of a reaction, any kind of delta, is final minus initial, or products minus reactants. So our products, negative 2630, minus our reactants, negative 2583. Whoops, 2583. Don't forget that when you subtract a negative, it's the same thing as adding a positive, or you could actually just put subtract a negative in your calculator, but subtracting a negative is the same thing as adding a positive, and this gives you a negative 47 kilojoules, okay? So I could take negative 2630 minus a negative 2583, and you'll get negative 47. Moving on. Ooh, one of my faves. Okay, it says a piece of metal weighing such and such is heated to a temperature of 88, immersed in water, etc. Okay, so we have a hot piece of metal, and that metal has a mass of 155 grams. And we heated it up to a temperature of 88.0 degrees Celsius. Okay, I'm gonna pause this for a second. Okie dokie, we're back. So we took this hot piece of metal. It started off as a warm piece of metal, and we submerged it into some water. Now the water seems to have a mass of, oh, excuse me, the metal, that's so annoying. This was 57.3. The mass water has a mass of 155 grams. Sorry if you were screaming at the computer right now. So 57.3 is the metal. The water has a mass of 155 grams. You took that hot piece of metal and you put it into the water. The water has an initial temperature of 21.53 degrees Celsius. And it says after equilibrium, the temperature is 24.72. And hopefully that makes sense because we took this hot piece of metal, we put it in the water, it heated up the water, right? And it got colder itself. So the final temperature for both of these is exactly the same because they're equilibrated, and it's 24.72. Okay, it says if the C of water is 4.184, what is the C of the metal? Oops. Okay, so let's talk about it. Anytime you have two things that you're mixing together where heat is transferred from one thing to another, you're going to think about Q equals MCAT, but for both of them. So hopefully you agree that the Q of the metal, the heat that the metal gave out, so the heat that the metal lost is equal to the heat that the water gained. Okay, the heat that the metal lost is equal to the heat that the water gained. And remember that Q equals MC delta T. So our negative MC delta T for the metal must be equal to the positive MC delta T for the water. Okay, so negative MC delta T for the metal is equal to the positive MC delta T for the water. And now we can just kind of plug and chug things in. First, let's go ahead and calculate these delta T's. Our delta T here equals T final minus T initial equals 24.72 minus 88.0. Okay. And I get negative 63.28. And then our delta T for the water is T final minus T initial, which is 24.72 minus 21.53, which is 3.19. All right, so now we can just kind of plug and chug into this formula here. Our negative mass of the water would be negative 57.3 grams times C, which we're solving for. So I'll just start putting these things in parentheses, times our delta T, which is negative 63.28, which is helpful because a negative times a negative becomes a positive, so those can cancel. We set that equal to the mass of water, 155 grams, times the C of water, 4.184 joules per gram degree Celsius, times its temperature change of 3.19 degrees Celsius. All right, so we're trying to solve for this one. So remember, you start with the multiplication on this side. You do 155 times 4.184 times 3.19. Now I want to get C alone, so I'm going to divide. You could divide by either of those numbers. I'm going to divide by 57.3, and then I'm going to divide it again by 63.28 to bring the other one over. And that leaves me with C equaling 0.571, which is why that is the answer. In terms of units, if we went and did this, the grams cancel, the degrees cancel. And here we have just joules, and then you divided it by grams, and you divided it by degrees Celsius, and that's why you get joules per gram degree Celsius. All right, moving on to this next one. It says, which of the following substances with specific heat capacity provided would show the greatest temperature change upon absorbing heat? Okay, pet peeve of mine. Let's go over it real quick. It says greatest. Greatest. Okay, what greatest means is the most, right? So you're looking for something that either is one of the highest numbers or one of the lowest numbers. Now they're all 10 grams, so it's all like the same amount. So the numbers that changed are this over here, okay? So you know right away, it's either this one or it's this one. That's the highest number, that's the lowest number. You have a 50-50 shot anytime I ask a question about the greatest or least, okay? Just keep that in mind. So we got a 50-50 shot. It's one of those two answers. Next, we could kind of reason it and say, hey, if you heat up water versus heating up metal, I would much less likely want to grab the metal because it's hot as Hades. So that is why it's your answer. But let's talk about what this means. This is the amount of heat. The amount of heat to raise 1 gram of the material 1 degree Celsius. So if you have a little gram of lead, it takes very little heat to raise it a degree Celsius. As opposed to water, it takes quite a bit times more, right? 40 times more to raise 1 gram of water 1 degree Celsius. So if you apply the same amount of heat to a little bit of lead or a little bit of water, that same amount of heat heats up the lead quite a bit more than it would the water. And that's why that is your answer. Okay. What volume in milliliters will a sample of F2 occupy at this, etc.? Okay, so here I see an ATM and another ATM. When I see two pressures, two temperatures, two volumes, I think P1V1 over N1T1 equals P2V2 over N2T2. But I didn't see anything about mole. I didn't see anything about temperature. So essentially our equation is very simplified. P1V1 equals P2V2. Super simplified. All you have to do is kind of plug and chug. Our initial pressure and initial volume was 1.2 ATM. And our initial volume, even though technically we don't have to change it from milliliters here because you'll get back milliliters, it's a good habit to be in to remember that if you have milliliters, you should usually put it into liters. So I move that decimal 1, 2, 3 times. And we set this equal to our final pressure of 5.5 ATM. And we're solving for V. Like we've done pretty much this entire exam. What we do is if our variable we're trying to solve for is over here, you start with the other side. 1.2 times 0.025. And now we'll divide by 5.5 ATM. And it gives me an answer of 0.00545. It would have two sig figs though, because the 1.2 ATM, which would equal, if we move the decimal 1, 2, 3 times, 5.5 milliliters. Okay. Next it says, what is the mass of NO2 contained in a 13-liter tank at 4.5 ATM and 385 Kelvin? So here I have liters, ATM, temperature. I'm already thinking PV equals nRT because I don't have two pressures or etc. So I'm not doing this first question. I just have one set of numbers. It wants to know mass. This is, so we have pressure. This is 4.58. We have volume that's 13.0 liters. We don't have the number of moles. We know R is 0.0821 liters ATM over mole K. That's just something that we need to know. It will, it may or may not be given to you on the exam depending on the semester, but it's just the gas constant R, and then times the temperature, 385 K. So we don't know mole, but we can certainly solve for it. If we know mole, can we figure out the mass of NO2? Hopefully you agree we can using the molar mass, which should have been given to you. The molar mass of NO2 is 46.01 grams per mole, but even if it's not, you could add up the mass of a nitrogen and 2 oxygens to get that. Okay, so let's solve for it. We're starting with the 4.58 times 13 liters, because this is the side that we're solving. This is the side that has the variable, so we start with the other side. I'm going to divide it by 0.0821, and I'm going to divide it by 385. I get an answer of 1.8837 mole. Be careful, because many of you might have grabbed this one right away thinking maybe you were off on a decimal. But this is mole, right? Not grams. So now we take that number and we multiply it by the molar mass. We know a mole of it has 46.01 grams. And that's where I get an answer of 86.7 grams. All right. Moving through. It says a sample, 0.334 gram sample of is unknown, so we can't put this in a mole because we don't know what it is. Occupies 109 milliliters, so we have a volume, we have a temperature, we have an ATM. volume, temperature, ATM. I don't know what we're doing, but I'm pretty sure it's PV equals nRT. And let's figure out mole real quick. So we're trying to figure out what kind of halogen this is. It gives you some hints. It says molar mass or grams per mole. You're given grams, find the moles, and then you can figure out the molar mass and therefore match it with this. But let's go ahead and find mole first, just because that should be your first instinct on this one. 1.41 ATM for the pressure times the volume of 0.109 liters equals N times 0.0821 times the temperature, 398. Okay, remember, we're trying to solve for N here. So we take what we got, 1.41 times 0.109, and we're going to divide by the point, oops, oh, what am I doing? 0.08, so I put 0.0821. Divide by 0.0821 and divide by 398. Hit enter, and that gives us the total number of moles. Okay, well, that's interesting. Thankfully, it gives us some hints, but even if we didn't, we know the moles, we know the grams, and we don't know much information about these things other than if we knew the molar mass, we could figure out what they are. So, molar mass has units of grams over mole. Therefore, we take the grams and we divide it by the mole. So 0.334 divided by 0.004703 mole. So 0.334 divided by the last answer gives me an answer of, oops, gives me an answer of 71-ish grams per mole, meaning my answer needs to be about 71 grams per mole. If you were to look at a periodic table, pull one off right here. These are all diatomics, okay? So I'm looking for something that has a mass of about half of this. In other words, something that has a mass of about 35.5. Half of 71 is 35.5. So I'm looking over here and I'm like, which element has a mass of about 35.5? Is it sulfur? Is it argon? No, it's chlorine. Bromine is way up there. So chlorine is 35.5. So if you had two of them, this would have a mass of 71 grams per mole. And that's why it's your answer. Okie dokie. Moving on. It says determine the volume of H2S needed to produce 55 grams. Okay, so it wants to know about H2S. So this is our question mark over here. And it gives us 55 grams of sulfur. We know 32.07 is the molar mass of sulfur, and that's grams per mole. So that would tell us our sulfur. 55 divided by 32.07 equals 1.7149 moles. 1.715. Okay, and that's the number of mole of sulfur. And it wants us to figure about H2S. It wants us to solve for volume. We know temperature and we know ATM, so if we can figure out mole here, we can plug it into PV equals nRT. So let's go ahead and do what we know. We know 1.715 mole of sulfur. For every 3 mole of sulfur, we get 2 mole of H2S. And that would give us our N for H2S. So I'm just going to keep the number I had in there, times 2, divide by 3, and I get an answer of 1.143 mole of H2S. Okay, and that would have 3 sig figs. This is how many mole of H2S we have. In other words, that's our N. So we can now take that number and let me get some paper. We can take that number and we can now solve for PV equals nRT, because PV equals nRT, we know our pressure is 1.20 atm. Our volume is what we are looking for. It equals 1.143 mole as our N, 0.0821 as our R, and then our temperature is 375 Kelvin. So this is the variable side. We start with the other side. We have this times 0.0821 times 375, and then I'm going to divide it by 1.2, and my volume is 29.3. You know that you're using the proper units, so it's liters. And B is your answer. Last but not least, I got a class to get to. I'm cutting it close, but we can do this, crew. Okay. Last but not least, number 14. It says, determine the percent yield with 21.8 grams. The first thing I do, turn grams into moles. 21.8 grams, I'm going to divide that sucker by 138.21. And I find out that this equals 0.3924 mole. Okay. So I'm going to rewrite this down here. Okay, where my number of moles here is 0.3924. Okay, and it says is produced from reacting. Ooh, wait, is produced. Is produced. Should I have written it there? It was produced. Oh, wait a second. This is my actual yield. So if it was actually produced, that's your actual yield, and that's good because it's asking for percent yield. Remember, the actual yield's always given in the problem. Our percent yield equals actual yield over theoretical yield times 100%. In other words, we actually know 0.3924 moles of K2CO3 is half of our problem. We're already halfway done. All right, so now let's go ahead and read it. It says from reacting 27.9 KO2. I put it in the wrong spot anyways. Looking through the camera lens instead of the paper. Okay, so 27.9 grams. We know I'm screwed up because I'm rushing. Oh, darn it. Sorry, guys. Over here, I should have done it. 21.9. Let's go ahead and take this. 21.9 divided by 138.21 equals. Okay, this actually didn't give me this. I wrote the wrong number. No wonder I was confused. This is 0.15845 mole. Cool. So this is our actual yield. 0.15845 mole. Sorry, if I don't finish this video now, it won't happen for another day. Okay, so this is the number of mole of K2CO3. That's our actual yield. Now, now we can go about this next one. It says 27.9 grams. 27.9 grams of KO, we divide it by 71.10 grams per mole. And this gives me the answer of 0.3924, which is why I had 0.3924 here. That's cool. Okay, so that's how many moles we want. Our actual yield was in mole of K2, meaning that's where our question mark needs to go. We need to figure out mole of K2. Okay, but we had some other information too. It's not just KO2, it also talks about CO2. And it tells us that with the CO2, that we have a certain volume, pressure, and temperature. So with CO2, we're given volume, temperature, and pressure. Just like we always take grams and turn it into mole, if you're given volume, temperature, and pressure, you also need to turn that into mole. using PV equals nRT. Okay. The volume given, well, actually, let's start with the pressure. The pressure given at STP, remember STP, is 1 atm and 273.15 Kelvin. So the pressure is 1.00 atm, or you could just do 1 with infinity. I do 1.00 to remind myself that I'm working with an actual number. The volume is 29 liters. I'm setting that equal to the moles, which I'm trying to find, R, which is 0.0821. I'm going to not write the units to save some time. And the temperature has to be 273.15 Kelvin. And this is all for the CO2. Don't forget what we're doing. So I'll take 1 atm, which we don't really need to write, times 29. I'm going to divide it by 0.0821 and divide it by 273.15 Kelvin to give me 1.29316. Okay. So now we're right back to where we were kind of an exam ago, where you have this and you have this and you have a question mark here. So anytime you're trying to find something over here, the very first step is find the limiting reactant. I'll divide this by 4, I divide that by 2, and I ask which one's smaller. Hopefully you agree 0.39 divided by 4 is smaller than 1.2 divided by 6. This, therefore, is our limiting reactant. So our limiting reactant is CO2, or KO2, excuse me. So I'm going to start with that. 0.3924 mole of KO2. I know for every 4 mole of KO2, I get 2 mole of the K2CO3. So 0.324 times 2 divided by 4 gives me 0.1962 mole of K2CO3. But what did we just find? Well, if you remember, anytime you have a limiting reactant, and then you figure out what you make over here, what you're figuring out is the theoretical yield, how in theory, that's the most you can make. That was our theoretical yield. So that's the number that we can use now to plug into here. 0.1962, and then of course times 100%. Don't actually use the percent sign. So 0.15845 divided by that last answer times 100, and we get an answer of 80.7%. If you put that theoretical yield back into grams, oops, 80.7. I'm sure I have a typo somewhere, but I don't have time, you guys. I think this is 0.15773. That's it. And this would give you 84%. Sorry to screw you up on the last one. Flight's got to go. Bye.